Okay, so I want you to notice what happens if I look at the same situation here with this elliptical paraboloid and the contour lines. I'm going to go ahead and take out those guys there. I'm going to take out the surface, and then we're going to look down straight upon it. Maybe zoom in a little bit. Can we do that? Yeah, we can do that. So watch what happens to the directional derivative here, right, which is in blue there. And watch what happens when I change it. And notice that, go down a bit. Notice that when I go left to right, notice that the unit vector is pointing straight up. So it's at pi over 2. Remember, our unit vector for this problem was right here. Cosine t sine t is how we created it, along with this u vector right here. So as we look, the gradient is in green, the unit vector is in red. Okay, and so as we go from left to right, notice the value of the directional derivative does not change, but as we go up and down, it does. Okay, so the value of the directional derivative is in blue here, so that what is going on here? So as we go up and down, it changes, but as we go left to right, it doesn't. Now, if I change, so notice that it's pointing straight up. If I change it, that's at pi over 2. If I change it to 0 or 2 pi, notice that when I go left or right, the blue dot changes, and as I go up and down, the blue dot does not change at all. Even though it looks like the directional derivatives change as I'm going up and down, the blue dot just stays constant. It's not 0, it just stays constant. It is 1.5, okay? And now if I let my u vector go straight up, 1.5, about 1.58 is about 1.57 is pi over 2, straight up. Then as I go left to right, the blue dot doesn't change. That's my directional derivative, even though it kind of looks like these two are changing with respect to each other, and that's how directional derivative works, right? But I want you to notice that the directional derivative, the gradient vector, is getting longer and shorter. So that may have something to do with it. Let's see. So the reason why this is happening is if you look at the surface and then the gradient vector and the unit vector associated to it, if we find the directional derivative using those two vectors, we're going to get x cosine t plus 2y sine t. And so when t is 0, sine is 0, so this whole term is gone. Cosine is 1 at t equals 0, so we're just going to get x for our directional derivative. So if we move in the y direction when t is 0, if we move in the y direction when t is 0, nothing's going to happen. It's going to stay the same. And if we move, similarly, if we move in the x direction whenever t is pi over 2, we're going to get the same value as well.